All right, let's go ahead and start our next unit. A very important topic in chemistry called kinetics. So there's a couple things that we're going to look at in this unit. One thing is reaction rate. So when we think of kinetics, we often think about the rate at which a reaction occurs. So how fast that reaction is occurring. We'll talk about how to measure that in just a bit. And then we'll look at also something called a reaction mechanism. A reaction mechanism, as we'll learn in this unit, shows how the reaction actually occurs. So keep in mind that a balanced chemical equation does not show how the reaction occurs. It simply shows what you start off with and what you end up with. It does not show how you go from reactants to products. That is the job of a reaction mechanism. So let's look at how reactions occur. And what we're going to look at here is something called the collision theory. Now, there's three things that must happen in order for a chemical reaction to occur. So first thing is that the particles, and by particles, we're talking about the reactants, whatever the reactants are, those could be molecules, could be atoms, could even be ions in solution. In order for those reactants to form products, the first thing is they have to collide. They have to come into contact with one another. Now, something to keep in mind is that not all collisions between reacting particles result in the formation of products. So B and C in the notes here are kind of the conditions for that collision to result in the formation of products, aka a chemical reaction. All right, so condition number one is that the particles must hit at the proper location or proper orientation or proper angle. Either of those will be fine in the notes here. We'll just say proper location. So here's the example. You have a reaction between a carbon monoxide molecule and an oxygen molecule. So if the oxygen end of the carbon monoxide molecule collides with the O2 molecule, no reaction will occur. Nothing's going to happen. Versus that we see below that, if the carbon end of the carbon monoxide molecule collides with the oxygen molecule, then a chemical reaction will occur where you're forming new substances. In this case, we get a carbon dioxide molecule formed, and we're left with also an individual oxygen atom. So that's condition number one. Condition number two is that not only must the particles collide and not only collide at the correct angle or orientation, but they must collide hard enough. They must collide with sufficient energy or force. So if the particles don't collide hard enough, they'll simply just bounce off of each other and remain as reactant particles, and they will not form new substances. So this again is known as the collision theory. Later on, when we talk about the factors that affect the rate of a reaction, we'll want to think about this collision theory, the things that, factors that affect the number of collisions. Of course, hopefully it makes sense that the more collisions there are between reacting particles, the faster that reaction will occur, the higher the rate of that reaction. So collision theory, very, very, very important. And be thinking about what things could affect the number of collisions between particles. Now, technically, there's two types of collisions, collisions that result in the formation of products and collisions that do not result in the formation of products. So any collision that does not result in the formation of products, we call ineffective. So there's lots of ineffective collisions that occur between reactant particles. Those collisions that do result in the formation of products are known as effective collisions. So again, we want to focus on the factors that affect the number of effective collisions, and then we'll talk about some of those things later. All right, so we said kinetics involves the study of reaction rates. What is rate exactly? There's lots of different examples of rates. We'll talk about what reaction rate means in the context of a chemical reaction. But in general, rates is change over time. So some sort of change over time. So a good example of this is velocity. Now we're not going to learn about, you know, velocity. We learned a little bit about velocity earlier in the year, but we're not going to really do any calculations involving velocity. But I just wanted to use this as a simple example to help you understand what rate means. So for velocity, it is a rate. It is the change in distance over change in time. So distance over time is velocity. So what is rate in the context of a chemical reaction? Well, rates refers to the time it takes for a reaction to occur. Now, um, the change that can be measured can be lots of different things. You could measure a change in mass. So let's say that you have a chemical reaction that occurs that forms a gas, and you let that gas escape to the atmosphere. Well, the mass of the system is going to change during the reaction, and you can measure that change in mass over time and get the rate of the reaction. Likewise, you can measure a change in volume over time. So again, for a system that involves gases, if you're producing a gas, let's say, you can measure the change in the volume of the system over time, and that will give you the rate of the reaction. Likewise, again, involving gases, you can measure change in pressure over time. So if you're forming a gaseous product, the pressure inside your container is going to increase over time, and you can measure that. If you have an endothermic or exothermic reaction, you can measure the temperature change over the course of the chemical reaction, and that'll give you an indication of the rate of the reaction. Usually, though, we are measuring concentration somehow, some way. So change in the concentrations of the reactants or products. We'll talk about how exactly those change in just a bit, but you can measure that change over time, and that will give you the rate of a reaction. Sometimes we even measure the change in absorbance. So we talked about absorbance earlier in the year. Using the spectrophotometer. So you can measure how quickly the absorbance of your system changes over time. And again, giving you an indication of the rate of the reaction. So something to keep in mind is a little pet peeve of mine. Rates of reactions will increase or decrease. Please do not say that the rate is faster or the rate is slower. The reaction is faster, meaning it takes less time. If you have a fast reaction, the rate is high. So just be careful with that. So reactions are fast and slow, rates are high or low. All right, so something very, very, very important to understand, not just now, but later on as well, is that during a chemical reaction, the amounts, and again, that could be the masses, it could be moles, it could be concentrations, the amounts of the reactants decrease over time. So the reactants are being consumed during a chemical reaction, thus their amounts are going to decrease. So let's make a graph of amounts versus time, and this could be, concentration, it could be absorbance, it could be all kinds of things. So we're going to go with, let's go with concentration. And let's say we measure the time of the reaction in seconds. So let's say initially the concentration of some reactant is high. Over time, its concentration will decrease as it's being consumed. Now, interesting to note is that this relationship between concentration and time is not linear. The concentration does not change proportionally with the time. And so what we end up with is something like this. Oops, let's go down to zero there. Eventually you end up with no reactants, let's say. So this would be a typical graph if we graph the concentration of a reactant over the time of a reaction. So we get an exponential decay or a hyperbola. Okay. How about the products in a chemical reaction? So during a chemical reaction, the amounts, so masses, moles, concentration, the amounts of the products will increase. You start with none, and after the reaction, you have some. So their amounts increase. So again, let's take a look at a graph of, say, the concentration of some product over time. And again, this could be seconds, minutes, if it's a really slow reaction, hours. We'll just go with seconds here. So once again, we'll start with our initial amounts. So at time 0, probably should label that on this graph too, time 0, the very beginning of the reaction. In the case of a product, we have none. And as the reaction proceeds, the amount of that substance will increase. Once again, not linearly with time, but rather we get something like this. At some point when the reaction is complete, you reach a maximum amount of that substance that forms. Now we can use these graphs to calculate the rates of some chemical reaction. Now there's two different ways we can do this. The rate at the very beginning of the reaction, which first of all is going to be the highest. At the very beginning of a reaction, reactions occur at their fastest. So the rate is the highest at the very beginning. The rate of the reaction at the very beginning is known as the initial rate. Now we can calculate the initial rate of a reaction using those graphs I just showed you by calculating the slope of a tangent line. So a tangent line being a straight line that touches the curve only at one point. In the case of initial reaction, that one point would be at time 0. So that's how we can calculate the initial rate of a reaction. Say we wanted to calculate the rate of a reaction, not at the beginning, but at some time during the reaction. We can do this as well. That is known as the instantaneous rate. The rate of a reaction at some instant, at some point in time during the reaction. So how do we do this? Again, we can calculate instantaneous rates by determining or calculating the slope of a tangent line at some particular time during the reaction. So let me show you what I mean. Let's go back to our first graph. And let's say we want to determine the rate of the reaction right here, whatever this time is, time X. And so what we would do is we would, first of all, go to the curve at time X, and we're going to draw a tangent line. So this line has to only touch the curve at this one point. It cannot cross through the curve. Now, I'm not sure if I'm going to be able to do this, but I'm going to try to draw a straight line. So let me try and do this and see what it looks like. Okay, so that turned out okay. It's better than I expected. So again, we can calculate. Here, I'm going to show in a different color, I guess. Let's do this. Change in Y over change in X, and that will give us our slope of that line. Now, what do you notice about the slope of this line? This line has a negative slope. So y2 minus y1 over x2 minus x1, we're going to get a negative value. If you have a negative slope, that means we have a negative rate. Not really, just that negative means that the amount of that substance is decreasing. You can show that with a negative. Now let's say we wanted to also determine the instantaneous rate at some other time. Let's say at time, I don't know, y. Time y. So go up to the curve right there. Once again, we're going to draw a tangent line at that point. So let me try to do that. Kind of hard to see, but I think that'll work. So once again, we have a negative slope. Speaking of which, notice anything about the slope of the tangent line at time y versus the slope of the tangent line at time x? Looks like the slope of the line at y is less than that at x. What does that mean? Think about what that slope is telling us. This is telling us rates, change in concentration over change in time. Make sure to include units in these calculations of slope. So we end up here with molar per second as our units for the slope calculation. So what this tells us also is that the rate changes over time. The rate is not constant over time during a reaction. So we have a different rate at different times. In fact, the rate is lower at time y than it is time x. Think about why that's the case. We could also do the same thing on this graph so we can determine the rate of the reaction at time x, let's say. Once again, we're going to get concentration over time, so molar per second. This time, what do you notice about the slope? Well, the slope is positive. So this is always a case when we're talking about the rate of a reaction relative to the amount of a product. The amount of a product is increasing over time, so the rate would be expressed as a positive value. Now, I don't want to go too far in the notes because we'll be doing an experiment where you will be investigating a couple factors that affect reaction rate. We'll be doing that with our famous clock reaction. This will give you kind of a good idea about what reaction rate is, how to measure reaction rates, and how reactions actually occur via thinking about the collision theory. All right, more next time. Thanks for watching.